Hello, my name is Sam from What the Hectagon Math Tutoring, and I'm here to present to you the solution to a related rates calculus question. So the question states that there's a person flying a kite where the kite is 80 feet vertically above the ground, and it is moving horizontally away from where the person is standing on the ground at a rate of 4 feet per second. And the question asks, at what rate is the angle theta between the string and the horizontal changing when the length of the string is 160 feet long? So what we're going to want to do to answer that question is to start by expressing all of the lengths that you see here in terms of each other and create some formulas that relate them together. So the first detail that's given to us is that the distance in the horizontal direction x is changing at a constant speed of 4 feet per second. So we're going to express the derivative of x with respect to time as dx dt, as one does. And this is going to be equal to the fixed constant 4 because it's changing at 4 feet per second. We're also going to want to relate the length L to the horizontal and vertical lengths x and 80, which is not very difficult because this is a right triangle. So the hypotenuse L is going to be equal to the square root of the sum of the squares of the other two sides. So L is equal to the square root of x squared plus 80 squared. Since we're curious about the rate of change of the angle theta, we're going to want to represent theta in terms of the other sides as well, so we can use trigonometry to do that. So how might we do that? Well, we can see that the opposite side to theta is 80, and the adjacent side to theta is x, so we can say that the tangent of theta is equal to 80 divided by x by definition of the tangent function, like so. Now we want to find the derivative of theta with respect to time so that we can determine its rate of change at a particular moment. So let's apply the inverse tangent function to both sides of this expression so we can isolate theta. So we apply the inverse tangent to both sides and we get that theta is equal to inverse tangent of 80 divided by x. And now we can take the derivative of both sides with respect to time. So the left-hand side is just a symbolic change, right? We're going to get the derivative of theta with respect to time. And on the right side, we need to implement the chain rule a couple of times because we have a couple of nested functions going on here. So the first question is, what is the derivative of the inverse tangent of something? The derivative of the inverse tangent of something is just 1 divided by 1 plus that something all squared. So we put a space for something in parentheses, and that's being squared. What is our something? Our something is 80 divided by x. That's the input of the inverse tangent function. So we're going to get 80 divided by x all squared, like so. But now we need to use the chain rule, and we need to multiply by the derivative of the inside function. The derivative of 80 divided by x is simply negative 80 over x squared. That's the power rule in action. And then we need to multiply by the derivative of the innermost function, which is x. Remember, x is not just an independent variable here. X is a function that is a function of time, I should say. And we know the derivative of x with respect to time. It's exactly 4. So when we multiply by dx dt, that's going to be precisely the same as multiplying by 4. Now what I'm going to do is multiply all the numerators together. So we're going to get 1 times negative 80 times 4. That's a numerator of negative 320. Okay, and now in the denominator, we're going to see something very nice. We're going to have x squared, and that's going to get multiplied into this denominator here. And what happens there is we get a denominator of, well, 1 times x squared, so that's x squared. And then 80 divided by x, all squared, times x squared, is going to give us simply 80 squared, because the x squareds will cancel. So this is the derivative of theta, the angle theta, with respect to time, in terms of the length x. But also, we might be able to see that the denominator is x squared plus 80 squared. And what is that? That's precisely L squared. And what is L? L is the length of the string from the person to the kite. So what this really is the same thing as negative 320 divided by L squared. And this makes the problem really easy to solve from here, because what was the question? The question was, what is the rate of change of the angle theta in radians per second when the length of the string is 160? Now that's really simple, because now we just need to plug in 160 for L. And so we get negative 320. What's negative 320? Negative 320 is the same thing as negative 2 times 160. So I'm going to express the numerator as negative 2 times 160. And since the length of the string at this moment is 160, we can put 160 squared in the denominator. And now the simplifications are easy as pie. We simply cancel one of those 160s with a 160 in the denominator, and we're left with negative 2 divided by 160, which leaves us with a final answer of negative 1 over 80 radians per second. And you can spot check this, because the angle must be decreasing over time. As the kite moves farther and farther away from the person, this angle will be getting smaller and smaller and smaller, which means it must be decreasing over time, which is to say that its derivative with respect to time should be negative. So the final answer of negative 1 over 80 radians per second not only makes sense, but it is also the correct answer. Thank you very much for watching.